Hi, my name is Philip Clinton, and this is my demonstration for Lab 1 on constant velocity for Physics 2211, Section M. In this specific experiment, the goal of the scientist is to observe an object that is experiencing constant velocity, with no sign of change in direction. For an object to stay at constant velocity, whether it be motionless at 0 meters per second or moving much faster without changing speeds whatsoever, there must be a net force of 0 on the object. Going further into detail, this means that the object or the system is not impacted by any of the surroundings, or better put, all of the forces on the surroundings or by the surroundings on the system cancel each other out. For my specific experiment or observation, the system was a marble, and the surroundings were the friction of the countertop, the effects of gravity, and the normal force. To portray the findings, the best way to determine if an object has a constant velocity is by looking at its position versus time graph, or position as a function of time. In doing this, each graph will produce 41 points on a line, demonstrating the observed and predicted distance for 41 frames of the video. When looking below the surface level of these observations, everything comes back to Newton's second law. Going further into detail, Newton's second law describes the idea that an object will either stay in motion or stay at rest unless another outside force acts on it. Thus, for an object to stay in the exact same speed of motion, there must be no outside forces from the surroundings, or they all must cancel each other out. Elaborating on the equation below, it further explains why a net force of 0 will not allow the object to change velocity. Given that the impact of the change in the amount of time is dependent on the magnitude of the force, a net force of 0 will always result in the same speed, where initial velocity is equal to the final velocity regardless of the time span or amount of time. Before arriving to the graphs and physical demonstrations of the lab, allow me to elaborate on why we can use this position as a function of time graph. When we look for velocity, the easiest way for this to be understood is the derivative of position, or position divided by time. The reason this works is because we are attempting to analyze something's speed or velocity, which we are going to say they're going in meters per second. Thus, they are going a certain distance or a certain amount of positions during a period of time, which allows us to safely set up two line graphs to demonstrate the differences. For my specific experiment, or position as a function of time graph, I chose to use a marble rolling across a countertop. While originally an individual may believe the aspect of friction would inhibit velocity, I believe that due to the extreme smoothness of the marble and the countertop, which also happen to be marble, friction would have a minimal to no effect on the constant velocity. Thus, in doing this, I recorded the video of the marble rolling across using my phone, which records the video at 30 frames per second, or a frame every 0.033 seconds. In this specific setup, I've placed the origin of the coordinate plane to be approximately the center of the marble at frame number 60. In doing this, because the marble is rolling to the right, we can say that its velocity has a positive x direction based off where I put the axes, as well as its change in position. By showing this, we can know that the velocity and position vectors, aside from potentially a slightly off the original mass location, there should be no negative values. When looking at the demonstration of the model we created in GlowScript, we can see that the velocity of the predicted position is correct in the positive x direction. While it is very simple to see that they both travel in the positive x direction undoubtedly, meaning the observed position and the predicted position, it further demonstrates that with the conditions of no net force, or a net force of 0, the marble has traveled farther in the predicted idea than the observed. Rather than rely on our calculations, the Python script not only proves that my calculations were correct, but also proves that my assumptions that the minimal friction would not affect the position was very incorrect. After finishing the analyzation of the data and models, we can begin to analyze why the results look the way they do, and what we could have done to create better results. As discussed previously, the observed position of the marble covered a shorter distance than the predicted position. This primarily can be attributed to friction, which, although I knew existed, I did not think it would influence the results to the extent which it did. Before explaining how we could possibly determine the amount of force the friction of the surface exerted on the marble, we need to look at all the forces that have an impact on the marble. In this experience, or motion of life, there are 4 forces that were acting on the marble. The original start, or push of the marble, the force of gravity, the normal force of the countertop, and the force of friction. Going into further detail, these 4 forces go into pairs, with the force of gravity and the normal force going in the y direction, and the original push and the friction impacting the x direction or x component. Prior to analyzing the x direction, we know that there is no net force of 0, or there is a net force of 0, in the y component for two reasons. The first is that we simply know that there is no moval in the marble in the y direction. There cannot be a y component. Rather than just rely on visuals, we also know that the force of gravity and the normal force of the countertop cancel each other out. Because the marble is not sinking through the countertop and is not levitating in the air, the normal force and the force of gravity must cancel out. Getting back to the forces in the x component, after the fact, I've come to the conclusion that there was indeed a non-zero net force in the marble. Although this shows that the marble was indeed not in constant velocity, we can once again use Newton's second law equation to determine the magnitude of the net force. Because the ball was slowing down or covering less ground than the predicted position, we know that the force is in the negative x direction. Overall, although the marble did not engage in constant velocity, we were still able to use the position and velocity equations from Newton's second law to determine the net force on the marble. If I were to repeat this experiment or situation again, I need to find a way to supply an additional force in the positive x direction. There are endless possibilities, but an example would be a fan that blew air in the positive direction behind the marble, or some sort of pulling system that pulled it in the positive x direction. Thank you.